Hey guys, Mr. Backerberg here. In this video, we're going to take a look at the chain rule. So as we're looking at the chain rule is probably one of, if not the most widely used differentiation rules in math. So the function y equals 6x minus 10 can be factored by taking out a GCF of 2. So then it would be y equals 2 times 3x minus 5. And because of that, we can think about it as a composition of functions. We could have the function y equals 2u and u equals 3x minus 5. And what we want to do is look at the derivatives of all three of these functions and see how they're related to each other. So we're first going to look at that equation y equals 6x minus 10. And we're going to find its derivative. So we can say that dy dx, if we find the derivative of this, if we differentiate that 6x, that's just 6, and if we differentiate that negative 10 on the back end, that just turns into 0. So dy dx, the derivative of y with respect to x, is 6. Now we can also look at this y equals 2u equation, and here we're going to be deriving dy du, since u is our variable in here. So if we do this differentiation, deriving the 2u, we're just going to get 2. And then we've got one more equation to look at, this u equals 3x minus 5. And if we do that derivative, this is going to be du dx, because it's the derivative of u with respect to x. If we differentiate that, we just get 3. Now we're looking for some sort of relationship in here between all three of these derivatives. Well, one thing I know, if we're just thinking numerically, is we know that 6 is equal to 2 times 3. So if we use what we know about each one of these individual derivatives, 6 was our dy dx. So I can take dy dx and plug that in for the 6 there. 2 was our dy du, and 3 was our du dx. And it's no accident that this relationship is happening with all of our derivatives. As we dig a little bit deeper into what the chain rule is actually saying, we'll maybe see a little bit more how these derivatives are related to each other. So this is a similar example. We've got the polynomial y equals 9x to the fourth plus 6x squared plus 1, and that can be factored into y equals 3x squared plus 1, all being squared. And so we can think about that as being a composition of functions as well. So we've got the y equals u squared function being composed with the function u equals 3x squared plus 1. And again, we're going to look at the derivative of each one of those individual functions and see how they're related to each other. So if we start with the equation y equals 9x to the fourth plus 6x squared plus 1, and we find its derivative. So this is dy dx. This is going to be 36x cubed plus 12x. Looking at our second equation, y equals u squared. If we do the derivative here, dy du, then that's going to be 2u. And then if we look at our last equation, u equals 3x squared plus 1, and we do du dx, we differentiate that one, and we're going to get 6x. Now, if we look for a similar relationship here, on the previous slide, we said that dy dx should equal dy du times du dx. So, based on what we've got, hopefully when we do a little bit of algebra in here, we end up with this relationship happening. So our dy dx was the 36x cubed plus 12x. dy du was 2u times our du dx was 6x. Now there's a little bit of substitution that we have to do in order to make this relationship work. We know that our u value is 3x squared plus 1. So I'm going to take that and plug that in for u. So then this is going to say 36x cubed plus 12x is equal to 2 times 3x squared plus 1 times 6x. And if we look at simplifying down that right-hand side, if I distributed this 2 in, I would get 6x squared plus 2, but then I would still have to multiply by this 6x on the outside. So then I'm going to distribute that 6x in, so I get 36x cubed plus 12x, which is exactly what we have on the left-hand side. So what happened here was the derivative of the whole function, that's our dy dx, that's the derivative of the whole function, it was equal to the product of the derivative of those two smaller individual functions that we looked at when we thought of this as a composition happening. So as far as what the chain rule actually says, it says that if f is a differentiable function at the point u, which is some g of x function, and g is differentiable at a specific x value, so then the composite function f composed with g of x, which really just means f of g of x, is also differentiable at that x value. So the way the chain rule is going to work is when we're doing this derivative for a composition of functions, we derive the outer f function, but we leave the inner g function the same, but then we have to multiply by the derivative of whatever that g function on the inside is. And using the chain rule takes some getting used to, but we'll practice it a lot and try to get used to what's happening in here. So in this equation, we're going to look at actually applying the chain rule. So we've got an object moving along the x-axis so that its position at any time t greater than or equal to 0 can be given by the function x of t equals the cosine of t squared plus 1. And we want to find the velocity of our object as a function of t. Now, how I know that we need to use the chain rule? I see two different functions happening. And a big clue here is that set of parentheses. So we've got this cosine function on the outside of our parentheses, but then we've got another function happening inside of the parentheses. So those parentheses are a big clue to me. So to do the derivative here, if we want to find x prime of t, the way the chain rule worked was it said we were first going to take the derivative of that function on the outside. So the function on the outside is the cosine. And if we do the derivative of the cosine, that's negative sine. Now, attached to that, we're supposed to leave the stuff inside of the parentheses alone. So this is the first part of the chain rule, but then we're supposed to multiply by the derivative of whatever's inside of those parentheses, that inner function. So if we differentiate the t squared plus 1, we're going to get 2t. Now, to clean this up a little bit, since we're multiplying, I'm actually going to bump that 2t to the front. So I'm going to say that my x prime of t is negative 2t sine of t squared plus 1. So that's using the chain rule. We took the derivative of the outer function, but left the inside stuff the same, but then multiplied by the derivative of that inner function. Now, some people like to call the chain rule the outside-inside rule. So if we're thinking about our composition as f of g of x, where we've got this outer function and this inner function, the chain rule, like we've been doing, said do the outside derivative first, differentiate the outside function, but then leave the inside stuff the same. So we're evaluating it at the inner function, but then as a multiplier, we attach the derivative of whatever that inside function is. So looking at this example, we're going to differentiate the sine of x squared plus x with respect to x. So the chain rule said do the derivative of the outside function. So the derivative of sine is cosine, but we're going to leave the inner function the same here. But then, as a multiplier, we need to attach the derivative of the inner function. So if we differentiate what's happening in there, x squared derives into 2x, and x differentiates into just 1. So the derivative here is the cosine of x squared plus x times 2x plus 1. That's going to be it for this video. Thanks for watching.